longtime collaborator on paleoceanography in the Gulf of Mexico, but his interests are actually quite broad. And if anyone listened to his interview recently on Michael White's podcast, you'll know that this study sort of arose from some water cooler talk, so a little bit far afield from what he normally does, but an interesting study for sure. And without further ado, I'll leave it to him.
All right. Well, thank you, Julie. That was a kind introduction. Feel free to interrupt at any point in this talk. As Julie said, I'm now at Brown as of 2 weeks ago, so New England's a little bit different than Texas. So this, as most of you would probably not have heard the podcast, this actually did come up where I was actually looking at some sort of temperature data and trying to look at heat sort of extremes as well as heat waves, quote unquote. We came to find out that heat wave is a politically very difficult term to really use, but heat extremes in sort of Southeast Asia, South Asia, coming from Bangalore, if you have a delayed monsoon onset, you actually tend to have a lot of heat extremes. So this was going on in 2015 and 2016 as well. And so I was kind of looking into it. I wrote a blog article about it. And it just so happened that we hired Pedro Dinezio from University of Hawaii, who's a PhD student from Rasmus in Miami. And he is a climate modeler and was interested in sort of attribution, global warming, things like that. So we started talking, and then we started doing some analysis, and this paper and work literally came out of sort of just random talking and sort of sharing of interests. So that's what I'm going to be talking about. It just got published recently, so you can look out for this paper. So I would like to thank my collaborators on this project. So Pedro, Yuko Okamura from UT, and then Clara Desser from NCAR, and a couple other people who helped me out quite a bit. So as I said, the motivation for the study came from April 2016 specifically. So April 2016 was a pretty crazy month in Southeast Asia. And what I have here is a figure from MODIS, which is a satellite that measures land temperature. And what we have here are land surface temperature anomalies for 2 weeks in the start, so April 1st to 2 weeks of April. And you are reading this correctly, that this is a 12 degrees C anomaly. So whopping heat anomalies. And so you can see all over here, and actually kind of shifted later on towards the end of the month over here. You see also in southern India, southeastern India. But for today, the focus of this talk is going to be on mainland Southeast Asia as opposed to maritime Southeast Asia. So this entire region right here that composed of Thailand, Cambodia, Vietnam, parts of Malaysia, and just this entire region which got completely, massively hit by this extreme heat. And it was so massive that not just NASA noticed, but a lot of other people noticed. This is a picture from the Chicago Tribune, which picked it up, and there was a bunch of other articles. But essentially, there were animals that were falling dead in zoos, people that were dying, but the animals got the press in this case. But the tigers are getting meat popsicles. We'll freeze pork legs and chunks of meat to feed them and cool them off at the same time. Outside of sort of animals, there were widespread agricultural impacts. It actually broke the record in 3 different countries for energy consumption. And this was unprecedented. People had not really seen this. And it had a lot of widespread impacts. So this is kind of the other motivation for us to study it is like, okay, these sort of extreme events in the tropics where it's usually, even though it's warm, it's usually wet, but what's going on here when you have dry heat that completely disrupts society and has far-reaching economic consequences. So we wanted to look at this, investigate this, because as we all know, one thing that we were looking at is that this heat event, April 2016, happened after the peak of a giant El Niño that occurred from 2015 to 2016, peaked in December. So the idea, so what's going on here? Can we predict? Is this sign of things to come? Can we predict these things? Why did this happen? All these interesting questions over water room banter, water cooler banter. So the idea is we know there's natural climate variabilities, very simple artistic plot that I put up here, and we have anthropogenic forced component as well of temperature change, which is kind of linear, at least the forced part. So the idea is that we wanted to explore, especially in context of this, was so what kind of nonlinear interactions occur with this sort of interaction between natural variability and anthropogenic variability, and how do they feed back on each other? And so we wanted to try and understand this. Of course, as we know, Southeast Asia, the mainland is in the deep tropics, and the biggest mode of natural variability, at least on sort of intraannual to multi-decadal timescales, is the El Niño Southern Oscillation. And how does that interact with anthropogenic climate warming to produce these giant, heat events? So just to do the drill, to do the due diligence, the El Niño Southern Oscillation, for those of you who may not know, is basically naturally occurring quasi-oscillation in the climate world in the tropics, where normally you have winds that go, trade winds that go from the eastern equatorial Pacific towards the west. You tend to have convection in the western Pacific warm pool, and you have rain and sort of normal quote-unquote picture. And then when you have El Niño conditions, you tend to have a reversal of the winds. You have a drop in the thermocline, and then you basically shift your convection to the Central Pacific. And this tends to wreak havoc throughout the world and has a lot of teleconnections, affects anomalous patterns of rainfall and temperature. And it's, I'm sure most of you know about this over here, so I'm going to quickly skip past this. But here you go, just as a summary slide. Normal conditions. La Nina conditions is when this normal mode tends to get more energized than it normally is. And the El Nino conditions is when you have a reversal of the winds. And that is just a pretty plot of sea level fluctuations that occur along with this. So huge imbalance of heat. And this tends to happen on a quasi-periodic nature. So if you take a spectrum of temperatures right here in the Central Pacific, you tend to see that they'll peak from the 2 to 7 year, 1.5 to 8.5 year band. And so this is natural variability. There's been debates about when it started, how long it's been happening, whether it changes continuously, whether it's forced or unforced. This is a different topic on itself. What we know is that this happens. And we know that one of the biggest events happened during 2015, 2016. It almost rivaled the classic 97-98 El Nino. And it had impacts all over the world on fisheries, on different types of things. And so the idea is, can we relate it to what happened in mainland Southeast Asia? And more so, can we actually clearly define the interaction between natural variability and the anthropogenic force component? So the kind of motivation for this talk is, what can we learn from the hot April? I'm going to refrain from using the term heat wave here, because heat wave tends to mean certain specific things in climate dynamic world, whereas it tends to apply mostly to the mid-latitudes. Nobody really talks about heat waves per se in the tropics, apart from India. So we were kind of sure, we wanted to make sure that we're not conflating terms here. So we're going to call it hot events or extreme heat events. So what can we learn from this hot April? As I said, we wanted to know what the interaction was with the 2015 to 2016 El Nino. And is there a precedent with respect to global warming? Can we try and extrapolate this to the future? And furthermore, if we extrapolate it to the future, can sort of focusing on events like this, can that tell us anything about predictability? Can it help the region? Can it help the socioeconomic impacts that it can have? And most importantly, can it alleviate it? Apart from sort of, these are all practical motivations, there's also an academic motivation that tends to is actually quite related to policy, the policy world as well. And the question is, has the signal to noise ratio of warming, of global warming, has it emerged? So just a little bit about this term emerged. Over the last couple of years, there's been sort of significant interest in this concept known as time of emergence. So you can see, I think I think Ed Hawkins had one of the first papers on sort of solidifying that term. The people have looked at it beforehand, but there's gotten a lot of press. There's several papers. There's actually many special issues dedicated to time of emergence, and many people are trying to understand when exactly can we pinpoint time of emergence. So what exactly is time of emergence? So what I have here, this is from a paper from Mora et al. This is, as you know, the plot of the sort of the subtropical Atlantic. That is the, I forget where exactly that is, but this is one point where they've extracted observations, which is in black right here, and modeling simulations of temperature, just monthly temperature, from that one point. Okay, so the time of emergence concept, what that means is, since we've had historical instrumental measurements of temperature, at what point do you have a year such that it's warmer than all of the preceding years? Very simple concept. So if you want to think about it seasonally, it's kind of like, when are you going to have a winter in the future that's going to be warmer than all preceding summers? One way to think about it. So, and this is kind of a shaky metric because you have a lot of natural variability. You have ups and you have downs. And so you can go, so for example here, as they say, you have the first 3 consecutive years out, but then natural variability pushes it back down. And then you go back up, down, and then it's like, oh, okay, you have 11 years, so maybe is that the time of emergence right there? And then you actually look into the future and it's like, actually, no, there's also these ups and downs that tend to force it back within that sort of baseline. And then in this paper, one of their interpretations is that, okay, so this red arrow right here, so whatever, 2030 or so, is when you actually have the time of emergence. What that means is this is the new normal. This is climate that natural variability has never seen before. And it's because of the emergence of the global warming signal. So it's kind of a very academic debate, and it's kind of a shaky metric because you tend to have natural variability. But it feeds back on policy because, you know, people, let's say mayors or, you know, city planners, they like to know this term. How much time do we have in terms of, you know, radically thinking about different approaches? And so it's kind of an interesting interaction between something purely academic and something that still carries a lot of weight in the media and policy. And so, yeah.
In this case, how did they come up with the baseline time length? Because, for instance, you have that year like around 1905 or something where it almost gets out of that gray area. Does that play a role in it?
Absolutely. So the question is, for example, this right here almost peaks out of it. So how do you draw a line over here, for example? And these guys, there were like multiple comments written on this paper, and I agree with most of those. And the idea is that they just went with, when do we have instrumental observations? They didn't consider paleo, and they said, we're going to just consider instrumental observations as normality. And anything that exceeds that is going to be abnormal. And that's how they actually defined this top baseline, is because of this year right here, where they said, okay, you know, that's the warmest it can get because that's what we have recorded. So there are a lot of flaws with this, but it became such an important thing. This is from a Nature paper. It had like, it was the first time that a comment in a Nature paper had a news and views. So it was a BCA that came out, and they actually, just a side note, the comment actually showed that this metric, so what they did, these guys, this paper, they went and did this for multiple different points. So they went and did it in like Key West, certain hotspots like Great Barrier Reef. They said, okay, this is going to affect ecosystems. I mean, and they have a valid point, is that you have a completely new normal that these ecosystems don't know about, that, you know, there's going to be rapid temperature. But what they did is they went into the CMIP5 archive and they started pinning numbers. So they said New Orleans is going to have climate departure in 2032. And so and the press took that up. So what the comment, Ed Hawkins and others showed that this year is actually very, very dependent on how long the simulations go on until. If you run this till 2400, you could have a year somewhere there that dips below it, which makes it a meaningless type of purely academic debate, but it's kind of a hot topic. Like amongst these, there are guys like, I mean, you know, there's climate dynamics. Is there different subcategories in paleo? There are emergence people. in like their, the climate dynamics fields, So, and they have heated discussions and whatever. So I'm a newcomer to this, so I'm coming in, I'm trying to be like, so, tying this back to the mainland Southeast Asia stuff, 12 degrees C anomalies is huge. So we were trying to look at, does this have anything to do with emergence? Can we say anything about emergence? This is from Hawkins' paper, which was before Mora's paper. Mora was here in Nature. Hawkins was in GRL. And I believe Mora didn't cite Hawkins. And so Hawkins wrote a comment on Mora's paper. But this is a very elegant plot. I really like it. This is October to March, ONDJFM averaged. This is going to be from, let's see, April, May, June, July, August, September, right? And what they did is they went in through all these climate models from CMIP5. It's an ensemble of climate models. CMIP3 at this time. And what they did was they did the same calculation where the signal to noise of global warming emerges greater than 1. That's how they defined the time of, I think it's a little more robust metric to determine it than pin it on 1 year. But they said, okay, if we do a simple mean over standard deviation signal to noise, when does that signal emerge? So in the colors that you can see are different years for different areas. And so you can see some very interesting things that pop out on a very zeroth order. So if you look at the poles and the mid-latitudes a little over here, they all tend to have times of emergences that are much, much closer to the end of the century. And why that is because the mid-latitudes and sort of the polar areas experience the greatest climate variability on the planet, right? You're not going to have as much changes. So for example, seasonal cycles itself is going to be much larger and amplified towards the poles. The tropics tend to be stable. They tend to have temperatures that are stable throughout. So that's where if you look at the climate models at least, they tend to show that maybe some of these tropical areas have already emerged, but if they haven't, they will emerge sooner rather than later because the signal to the noise is less, the variability is less, the signal is going to emerge a little faster. But we also know that on the flip side, the El Niño Southern Oscillation, that imparts the largest noise to the tropics. So this is despite that. And so one thing is if we look at the mainland Southeast Asia region, and this is April right here, right? So it's a 2016 event, a sign that mainland Southeast Asia has emerged. I think it's a very pertinent question, valid question, regardless of the academic nuances that are involved in this debate. The idea, if we can pin down via observations that some place has emerged, I think that was a big deal. So we dug into the surface temperature records. I will be referring to GISTEMP, which is the product from NASA, and CRU, which is the product from Climate Research Unit in UK. And so CRU, unfortunately, they only provide their product after the end of the year. So while it came out now, at the time of the study, they hadn't released 2016 yet. But NASA, they put it month by month. So America's better, right? So you can see 2016 April right there. And so if you just do sort of a rudimentary analysis, you can say, okay, is this a sign that mainland Southeast Asia has emerged? So it's way up there. There are some big things going on in the past. It's kind of spiky, whatever, but this is way, way up there. And by the way, just to clarify, I will be dealing solely with monthly average values. I'm not talking about daily temperatures. I'm not talking about weekly temperatures. I'm looking on a climatic level, okay? So more of a seasonal level in this case, to be precise, but I'm looking at monthly temperatures here. And despite that, the monthly average here it looks to be the highest. So the question is, has mainland Southeast Asia emerged? So this was another motivation driving the study, apart from all the practical nuance. So coming back to the April 2016 event, this is the sort of the monthly anomaly. So we went in, we got the satellite temperatures, and this was sort of the monthly anomaly. You can see that there are parts that were almost greater than 6-7 degrees in certain areas. The one thing to think about for this entire region, this is the seasonal cycle. And the seasonal cycle, you can see that April tends to be the warmest month of the year. Why that is that April, in this region, April tends to precede the monsoon. The monsoon onsets in May in this area, whereas in India, it's a little later on because the winds need to take about a month to go over. Where in India, the hottest month is May, and the monsoon onsets in June. Whereas here, April is the warmest month, heats up the land, and then you have the monsoon come in, cools it down pretty rapidly later on, right? So April is the hottest month, so it tends to be prone to extremes. It's already up there, it's already hot. And so the climatology itself, simple analysis shows that it's the warmest month of the year, prone to extremes. But we also want to know what happens to Aprils in this region during an El Nino year. And by during an El Nino year, we all know that El Ninos tend to peak in December, January, February. So right after the peak of an El Nino, what happens to this region? So very classically, this is an updated graphic from NOAA, but they're talking about warm episode relationships, aka during an El Nino, in the peak of an El Nino. So it's kind of known that this entire region gets warm. Some parts here, this is mainland Southeast Asia right here, but some parts here, the maritime continent tends to be dry and warm, sort of in this nexus of dry. And if you remember at the start, the convection moves from the Western Pacific to sort of the Central Pacific, so this place is sort of wet and warm. Has all sorts of impacts all over the world, but in this area, it's generally known that El Ninos tend to warm up this region. But this is, again, during December and February. But this is not something new. People have studied El Nino since the 82, 83 events and since Bjerknes in 69. So this is like a graphic from Halpert and Ropolevsky in 1992, where what they're showing here through arrows, different arrow directions, tend to show the highest impact. Which month has the highest impact post-El Nino? This would be pre-El Nino, this would be post-El Nino peak. And they all know that the highest impact in this, even with data way back then, even without big El Ninos, they sort of show that during April, or 4-ish o'clock, is when they have the highest peak departure. So during April, we expect this region to become warm, basically. And it's nothing new. The idea is to try and look at it in more detail. So again, here's the NASA product, the CRU product, and in purple I have the actual satellite product as well. And so this is surface air temperatures in mainland Southeast Asia post-1940, and this is all Aprils. So every dot here is an April. It's only Aprils. I'm looking solely at Aprils. And we actually dug into this a little bit. I'd be happy to talk more for people who are interested, but we wanted to look at actual records. We looked at the density of temperature records, the number of gauges in each place. And as you can imagine, during